40 days. That's how long our server was busy computing population figures before we turned to robots to speed up the process. So, hello everyone. I'm Jérôme from GeoPostcodes, and together with Daniel from Wherobots, we're going to present you an efficient infrastructure to compute demographic data. So, GeoPostcode is a location data provider existing for 15 years. We're maintaining global address data available both in point and polygon formats. Our latest product is the population database, which is giving historical, present, and future population estimates for each zip code area and each administrative division in all countries of the world. So, how do we build it? That's illustrated on the image on top. And it's basically leveraging the zonal statistics algorithm that was already introduced earlier today. So what we do is that we use reliable population raster that you can see on the left side of the animation. And we overlay our boundaries data that you can see on the right side. And then we aggregate, we sum all the raster values falling within each polygon. We do that for all the countries in the world, for 12 different years that are available as raster data. And the result is population values, density, and trends for all administrative divisions and zip code areas in the world. So let's look a bit further into our original implementation. So we leveraged the QGIS implementation of the zonal statistics algorithm. And what we did, which is pretty cool, is that we Dockerized QGIS. So we can run a headless version of QGIS without the graphical interface on any server. And the Docker container, of course, can access both the population raster and the boundaries data that are stored on a PostgreSQL database. We're only computing the zonal statistics for the zip code areas and the most granular administrative divisions. And then the less granular ones can be summed up knowing the children value. So that I'm going to illustrate that here on the right. So you've all recognized the beautiful state of Delaware, which is very convenient here, not only because it's a state with the smallest number of county subdivisions, but also it has a nice vertical shape fitting on this slide. So Delaware is subdivided into 3 counties, Newcastle, Kent, and Sussex. And so we run the zonal statistics on these 3 polygons, and we end up with roughly 650,000 people living in Newcastle, 200,000 in Kent, and 258,000 in Sussex. Now, if you want to know the total population living in Delaware, of course, we could recompute the zonal statistics on the entire polygon, but there is a simple way. We just sum up the value for the 3 children and end up with 1.1 million people approximately. So, yeah, with that, we were all set and ready to run computations on the 12 raster years, the 247 countries, leveraging our high-resolution administrative boundaries and zip code areas boundaries. That was a bit intense for our server. So the challenge is it took 40 days to get all the results. And of course, that's creating a few side problems. So first, it's delaying the product launch. Second, you need to monitor closely the computations, be sure that they are still running. And third, it's pretty annoying if you need to relaunch the computations for any reason, like a bug, which never happens to us, or a bit more likely, an update in the underlying data sources. So we're looking for a more efficient infrastructure, and we were attracted by Wherobots' approach. And so Daniel is going to present you the solution.
Thank you. So, just to reiterate, this process was taking 40 days. Imagine how much additional work you can get done if you can open up 40 days worth of your time. What Wherobots brings is the knowledge of Spark and Sedona as it was created by the original authors of the Sedona platform. We use our Wherobots DB that is affectionately called Havasu. This is the spatial extension to the iceberg tables. We bring a much better developer environment We offer spatial notebooks, which allows us to iteratively test and try out new ways of bringing this data together. And we offer lots of ways to then smartly, what was the word I'm looking for? Pare down your data and effectively and efficiently retrieve it. So what were the results of these experiments? We were able to drive their development time from 40 days down to a few hours. Looking at these numbers, we see upwards of 135x. Now, this is after a lot of iteration that we're actually able to do with this platform because of the speed at which we can process data. Some of the key improvements we had here were effective global partitioning. We had more efficient retrieval and materialization of the raster data as well. We were able to dynamically, on the fly, convert some of our values, specifically the zero population values, into our node data, further reducing the amount of data that we had to materialize from our process. Russia, if you notice, we have a kind of an outlier here with Russia. So everything you see is dramatically faster. I mean, we're running in under 10 minutes for each of these, but Russia, obviously here, is running just over an hour. And so we were really curious from a data science perspective, like why is this one taking so much extra time? And it really comes down to the distribution, right? This is the second largest collection of zip codes. The distribution of them both in size ranges from very, very small to very, very large. Which changes how we needed to partition our data and how we run this analysis. So for the future, when we start to develop more products and more work with GeoPostcodes, we're looking at other additional ways to subdivide this data and make this retrieval and analysis much faster. That's really the bulk of it. We're able to take these processes that are typically taking hours, days, or weeks, and within the Wherobots platform, we're able to drive that development time down to hours. Thank you.